Hello everybody, I will start OpenCV tutorial. Today's lecture is based on the OpenCV tutorial material created by Omni Perez. He adapted contents from the Gary Bradesky's material. He is the founder of the OpenCV and also he is author of our textbook. First, I will explain why the study of vision is difficult. The study of vision is the study of changing the input from the camera sensor to recognition. The reason the mission is difficult is that input signal from the camera are all a set of number. As you can see in the photo below, our eyes can see the car image and recognize the side mirror. However, in computer vision, it is necessary to analyze the sensor data of the numbers passed from the CCD chip to find out what these numbers mean to reach the recognition. Can you find the edges using the slope information in the matrix below? There are some difference in the intensity number. These edges are often used as important features for recognizing objects in the computer vision. But it is not always easy to recognize objects using these edges. Basically, edges are detected based on the intensity discontinuity in a picture. However, if there are several edges detected in an image, they can be interpreted as different meaning. This edge shows depth discontinuity. You can see the post is closer than the background. This edge shows the surface orientation discontinuity. This surface normal is here. This surface normal is here. This edge shows a white line on the asphalt road, which is a reflectance discontinuity. That is a surface material property. This is a white paint. This is a black asphalt. So there are discontinuity in reflectance. This edge shows a shadow, which is illumination discontinuity. Thus, even though we have edge information, it is still difficult to understand the image based on the edges. Another difficulty in vision is that we must deal with the lighting change. In the machine vision system, we need to set up the lighting environment and control it carefully. If you do not control the lighting condition, you will fail to recognize an object in the afternoon, even though you succeeded in the morning. In this picture, which square is darker, A or B? But two squares have the same brightness. Human eyes are quite adaptable to the lighting change, but machine vision is not. However, light is also strong clue to recognize an object. The upper image is a crater due to the meteorite collision. The lower image is a 180-degree rotated version of the upper image. The lower image looks like a mound. This image is a mirrored image of the upper image. It still looks like a mound. So lighting direction is very important. People are applying the perspective when viewing images. Perspective means that closer object looks bigger and the objects that are far from here look small. Additionally, since we are dealing with 3D object in machine vision, therefore even when viewing the same object, it is difficult to figure out what the actual object looks like, because the image varies depending on the point of view. There are two people in the picture on the right. You will feel that the height of a person far away and that of someone near you are almost the same, even though the image of the person behind is actually much smaller than that of a person in front. We still feel the height of these two people is almost the same. But how can computer vision find out these are at the same height? Next, we will explain the camera model and the lens and discuss the problem and the corrections. This picture shows a human visual model. Here is iris, and iris control the amount of light, and here is a lens, and here is a retina, and here is a fovea. Fovea that has a lot of optic nerves. The camera is a machine made by replicating the human eyes. The camera has a lens and CCD chip corresponding to the lens of eye and the retina of eyes. When a human eye look at the tree like this, after passing through the lens center, and the shape of tree is inverted on the retina here. But in my brain, we think the tree is upright, so there is some nerve connection is like this, and at the time the size of image of the tree on the retina can be calculated using proportional relationship between this large triangle and the small triangle. When the height of a tree is 15 meter and distance from the lens center to the tree is 100 meter, then the distance from the lens center to retina is 17 millimeter. Then we can calculate the height of the image using the proportional relationship of triangle. So 15 to 100 equal x to 16. So x answer is 2.55 millimeter. There are several mathematical camera models in computer vision. Here are A, B, C points in 3D world, and here is the center of the lens, and images of points A, B, C are A dash, B dash, C dash in the image plane. Although the images of A, B, C's are inverted in the image plane, it looks straight when we look at them on the monitor. Therefore, when performing various image-related calculations in computer vision, the image plane is brought forward by the focal length f to create a virtual image plane to solve the problem of image flip. So this is a real image plane that is located behind the lens center, but we bring this image plane in front of the lens center. So here is imaginary virtual image plane. The advantage of virtual image plane is when we look at the tree like this, and the image is not inverted vertically. In this case, there is some inverted image here. So this image is what we see on the monitor. Okay. Okay. In this way, the image formed on the virtual image plane is not flipped, but it is straight. That is the image that we see on monitor, so we can easily calculate it. We can set the origin of the camera coordinate system xc, yc, zc to the lens center. This is the lens center. And you can set the coordinate system with the right hand rule by setting z-axis to outside of the camera lens. Here is a lens, and we set the z-axis like this. Then we apply the right hand rule to assign the xc and yc here. So xc axis is a horizontal axis, and the y-axis is a vertical axis. At this time, the coordinate value when an arbitrary 3D point is projected on the image plane is expressed by these equations. X image coordinate is x divided by z multiplied by the focal length. Ys can be achieved like this. It's quite a simple equation. The coordinate system below model 2 is when the origin of the coordinate system is centered at the image plane. At this time, the coordinate value of the projected image is expressed by the following equations. So xs can achieved by x minus f. So this is the equation for xs. So difference is instead of using z, in this equation use f minus z. Here you can see the value of x and y have a negative value, which means the image of a point is flipped about the lens center. In the computer vision field, researchers have chosen and used one of these two coordinate systems. OpenCV used the first lens coordinate system. These are the matrix form of equations that calculate image coordinate from the world coordinate of the object. When x, y, z in 3D world is inputted, the x screen and the y screen are calculated using model 1 coordinate system. So this is input, and if we have focal length along x-axis and along y-axis, cx and cy is center of the CCD chips. So this is a geometrical center, and this is a CCD chips center. So there can be some difference between them. So by applying these equations, so we can get the x screen and y screen coordinate. So this is a matrix expression for this equation. So this matrix M is a very important matrix in OpenCV. So the finding out the fx and fy, cx, cy is the objective of our camera calibration procedure. The below box shows the equation for model 2. P is a projection matrix. It contains f focal length here. Because it used the homogeneous coordinate system, this vector is identical to this vector. So homogeneous coordinate system we will talk about the homogeneous coordinate system later, but you just remember that this is equal to this. So this divided by this will we will get this number, and the y divided by this we will get this number, and this divided by this results in the 1. So these two metrics are the same. So this is xs, ys 0, 1. So xs is like this, ys is this equation. In studying computer vision, you will meet this word aspect ratio. So the aspect ratio of an image is its width divided by its height. Width, height. So aspect ratio is width divided by height. So because we are the common aspect ratio is 4:3 and 16:9, so it usually greater than 1. Pronunciation of aspect ratio is x to y or x by y. The two common videographic aspect ratio is 4:3 or 16:9. 4 by 3. This is example of 4 by 3 aspect ratio. 640 by 480 or 1024 by 768 is you are must be familiar with that numbers. Maybe sometimes you are familiar with this number, but this 16 by 9 is the wide image. Another word you will meet in computer vision field is field of view. Field of view is angular extent of observable world that is seen at any given moment. So we write FOV in short. This is a field of view. A field of view can be expressed in millimeter or degree. This is a length. This is angle. Length has its own unit, but the angle does not have a dimension. It's just a degree or radian. First, let's think about the definition of a radian angle. Here is a circle here, and the radius is r, and the angle of theta angle is here, and L is arc between here to here. So this is definition of a radian angle. L equal r theta r. So theta r can be calculated by L divided by R. So this equation is equation for conversion from radian angle to degree angle. So 360 divided by 2 pi. So by multiplying this number to radian angle, you will get the degree angle. So theta r is L minus R. So this is the final equation for conversion. In the figure below, when the distance from the lens center here and to the target object is this is target object. This is a working distance. FOV can be expressed as a vertical FOV and a horizontal FOV, a diagonal FOV. So this can be expressed in millimeter length or degree angle. If the distance from the lens center to the target object is 1 meter, this is 1 meter, that is 1000 millimeter, then vertical FOV can be measured by ruler and get the length m is in millimeter. The FOV in millimeter can be converted into FOV in degree. This is equation. This equation is here. 300 divided by 2 pi, and L is 1. R is 1000 millimeter, and M is a vertical length. So actually, in this equation, L is arc from here to here, but the theta is very small. We can approximate this arc to the vertical length. So this is approximation. So by calculating this number, we can get the 0.0573. So if we have a field of view in millimeter, then by multiplying this number, then we can get the angle. This is equation for converting angle to millimeter FOV. Actually, FOV is related to the size of sensor width and height, and focal length. So if we have a bigger sensor, the FOV will become bigger, and if we use smaller focal length, then the field of view become much bigger. Longer focal length means a telescope lens, and shorter focal length is a wide angle lens. So when we set up some machine vision system, we define the working distance L. This is R, working distance, and we set up the field of view in millimeter. Then we select the proper lens, F or the CCD chip size. Then we can get we can set up the computer vision system. But another issue is working range. The camera should have a proper working range that have a focused area. So in order to work in this area, the image of object should be focused from here to here. So if we use a wider angle, this length, the range become bigger, and if you use a telescopic lens, the range that have a focused area become narrower and narrow. So it is a matter of selecting lens and camera type. In order to compute accurate image with computer vision, the camera system should be calibrated. That means it is necessary to improve the lens aberration. Lens aberration can be divided into geometrical aberration and the non-geometrical aberration. Geometrical aberration include spherical distortion, astigmatism, that is nanshi in Korean, and the tangential distortion, and the coma. Among them, OpenCV provide routine to correct spherical distortion and tangential distortion. So the picture on the bottom left shows spherical distortion, showing that the error is smaller at the center and center of image, and that then the distortion increase in proportional to the radius. Is the biggest error occur in the corner. So straight line become this way. Figure on the right represents tangential distortion, where the distortion occurs at the angle around an axis. This is a rugby ball shape. Two cases can be calibrated in OpenCV through a calibration routine. The non-geometrical aberration include chromatic and vignetting. These aberrations can be reduced by not using a single lens, but by using composite lens with multiple lenses superimposed, like this. For more information on camera calibration of OpenCV, please refer to page 644 to 648 in our textbook. By correcting image distortion through the camera calibration described above slide, we can approximate the actual lens acting like a pinhole camera. We mentioned that the actual camera has a composite lens to prevent non-geometrical aberration, but we assume that it acts like a pinhole camera. Do you remember pinhole camera? If you have a black box and if you make a very small pinhole, then here is a black box, and if you use a very thin white paper here, then you can see the image inverted here. All light pass through this point. From this light have an image at here, and the light from here, actually it travels all around the world, but only this light pass through this hole, and it get the image at here. So here, this is inverted image. This is a pinhole camera. All light pass only one point. This is the center of lens in ideal thin lens. The distortion can be corrected mathematically. First, we use the camera model to calculate position of a projected image of the target point. Then the actual camera is used to capture the image of target points, and the coordinate of the target points are measured. Here is a mathematical camera model that can be xs equal f xz, ys equal f xyz plus cx plus cy. So this is mathematical model. So if we know some coordinate of 3D points in the 3D world, then we calculate this image value using this mathematical model, and we take picture of actual this point. Then we take a picture and measure this image. Then there will be error between calculated position and actually measured position. So by applying some optimization technique to reduce this error between these two, then we finally get the fy and the cx cy. We calculate this proper value So that is calibration routine. In order to do that, we use the checkerboard like this. So by taking picture of checkerboard at some by giving some variation in position and orientation, then this is all capture the image of the checkerboard. Then they calculate this the exact value of the parameter fx, fy, cx, cy by in OpenCV. So they provide a calibrate camera subroutine in OpenCV.